Next induction problem is going to be a somewhat different flavor. We're going to talk about how you can use induction to prove inequalities. And here, we're trying to prove that 2 to the k is bigger than k for all natural numbers. So for all k bigger than or equal to 1. Now, like I said when we did the first proof of the Gauss summation formula, we should probably settle in first, just to see what happens. Okay. Now, if you remember calculus, you know that any exponential function grows faster than any linear function. So at some point, we know from just our calculus intuition that 2 to the k wins out when k gets very big. But we don't know when it wins out. And the claim is it wins out after, well, definitely is winning when k is at least 1. Okay, but let's do some computations first. So here we have a p of k, which is 2 to the k is bigger than k, and this p of k is a statement for all k bigger than or equal to 1. So we're going to settle in first by looking at what p of k is for various k values. Let's start off with the first one, 1, which will double later as being our base step. But when k is equal to 1, this is saying 2 to the 1 is bigger than 1. Certainly that's true. 2 is bigger than 1. When k is 2, what is it saying? Well, it's saying 2 squared is bigger than 2. Well, 2 squared is 4. 4 is bigger than 2. Check. Let's do one more. Let's do p of 3. And when k is 3, this is saying 2 cubed is bigger than 3. 2 cubed is 8. 8 is certainly bigger than 3. Check. So that's what this is saying. And we want to prove it for all natural numbers. And so we're going to apply induction because it's a statement about all natural numbers. So let's be formal. Again, proof. We apply mathematical induction. I've been trying to start these first sentences in a bunch of different ways. There's a bunch of different ways in how you can say we're going to use induction. But you should always tell your reader what you're doing, because the reader is not a mind reader, unfortunately. The base case, which is p of 1, we've labeled what p of n is, or p of k is, so we can write p of 1, is 2 to the 1 is bigger than 1, which is true. So the base case is fine. We then proceed for the inductive step. So for the inductive step, we're going to suppose p of k is true, which just means 2 to the k is bigger than k. And then we're going to show that p of k plus 1 is true. So that's 2 to the k plus 1 is bigger than k plus 1. And notice for the inductive step also that we're starting here at k is at least 1. This is not, it's good to know where your starting value is. You don't have to write that down. I'm just going to point that out because we're going to need to use that here in a minute. Okay, so we're starting with the truth of p of k. That's here in blue, underlined in blue. So since we know that we're assuming that that's true, we can say since 2 to the k is bigger than k, well, how do we create a 2 to the k plus 1? We put here as an aside, 2 to the k plus 1 is really 2 times 2 to the k. So if we have a 2 to the k, to create a 2 to the k plus 1 to try to get the left-hand side of our inequalities to match, we can multiply by 2. Let me not say since, because I'm not going to have a conclusion. I'm just going to say we have. So we're going to do some computations. 2 times 2 to the k is bigger than 2k by multiplying by 2. Multiplying by 2 does not change the inequality because 2 is positive. Our left-hand side is 2 to the k plus 1 by our observation earlier. And I'm going to choose to write our right-hand side as k plus k. Why write it as k plus k? Well, I haven't changed anything, and we're after something with a single k. So this is one way in which you can single out one of the k's here. And we know that actually, oops, let me copy that again, and then I'm going to add a step here on the right. I'm going to replace this k using our, it's sort of obscured up there, but we know that k is always at least 1. Okay, so since k is at least 1. And so if we combine, whenever you're combining inequalities, you have to accept the strictest inequality first. So if this was all bigger than or equal to, we'd write a bigger than or equal to. But since there's one strictly bigger than, that's what we have to accept. So 2 to the k plus 1 is bigger than, by reading from the left-hand side all the way to the right-hand side, k plus 1. And that's great. That's golden. Let's gold it. That's golden. So this is what we wanted to show, p of k plus 1. So we conclude then that p of k plus 1 is true. And that completes the proof by induction. Now, if you like, you can put a concluding sentence, that says something like, by induction, 2 to the k is bigger than k for all k bigger than 1, or something like that. But I'm just going to say it completes the proof by induction. And then I like to do the 2 slashes, as you probably noticed, but you can do whatever ending symbol you like. You should always put the ending symbol there. And so this is a slightly different type of example where we're playing with inequalities. And I personally, when I was a student, sort of struggled doing proofs by induction with inequalities. But it's good to be able to see induction in different settings.